Classes in Statistical Mechanics. Lectures by Professor George Phillies, based on his book, Elementary Lectures in Statistical Mechanics, Springer-Verlag, 2000. Lecture 8, Aside C, Gibbs Statistical Mechanics, and how he gets from statistical mechanics to thermodynamics. I'm Professor Phillies. This is the next lecture of the ISP on statistical mechanics. Today we're going to begin by discussing aside C, which is Gibbs' derivation of the core equation Q equals exponential minus beta A. We aren't actually going to work through this, and this is actually not his derivation. Gibbs' derivation is 150 pages long. Gibbs was an extremely spare writer. He said nothing in many words that could not be said in few. And so there will be at least one point where we are going to unpack a paragraph discussion of his to the point where you can see what he's saying, and it will take 2 or 3 pages. However, what in general did he do? What he did is to say, I am going to hypothesize that the Gibbs statistical weight, which he just called the statistical weight, is correct. And then I am going to do a few things. And one of the things he did was to introduce a quantity seen in equation C.3, page 112, which is called eta. Eta, as you would probably not know because he doesn't tell you, comes from the Greek entropos. It's entropy. And what he does is to show that eta has the properties you would expect of the entropy of the system under various sorts of changes. He also talks about the statistical weight, because what he said was the statistical weight was e to the minus e times 1 over theta. But what's 1 over theta? Well, it's not clear what theta is. So he takes 2 systems with different values of theta, and they can be ideal gases, and at first they're non-interacting. And then what he does is to say, we're going to add an interaction, and it's going to be a very weak potential energy, which we can turn on and off. This business of introducing an extra weak potential energy which comes and goes is the basis of charging processes, which we'll discuss in Chapter 20 when we discuss the chemical potential. The important issue, though, is what he does is to say that if we have 2 systems with different values of eta, and their particles are interacting, there will in general, not in every case, but in general, be a net flow of energy from one system to the other. The energy will flow from the larger system to the smaller system, rather the larger theta system to the smaller theta system. It will behave exactly like the flow of heat from a hotter system to a colder system. And he will actually discuss this, and he will get it to work. He will also introduce averages and say we have an average energy. And having combined all that, he will say we have an average energy, we have something that looks just like the entropy, we have theta, which looks just like the temperature except for maybe dimensional issues. And therefore, I can introduce something, A, which is E minus Ts, which behaves just like the Helmholtz free energy. And he actually works through those arguments. He does also talk about alternative forms for S in particular, or T. He doesn't tell you why he works through those alternative forms. What he is doing is working through the Boltzmann forms for the energy and the temperature. And what he shows is that for small systems, the Boltzmann forms don't work very well. But his forms work just fine, because Gibbs statistical mechanics is a theory which is equally good for large systems or small systems that are at the same temperature. The Boltzmann model, the Boltzmann treatment, works for an isolated system of which all states have the same energy. Well, if the system is really huge, you remember calculating fluctuations, at least for a gas. If the system is humongous, the energy fluctuations in the total energy of the system are very small relative to the total energy, and therefore more or less all the states have the same energy, and we just make the approximation. That's potentially dangerous, but it works in this case. But what he does is to go through and show that in all cases either his theory is better than Boltzmann's or they give the same answers. And that is how Gibbs marches through to treat this. Gibbs also discusses reversible and irreversible processes. In the Gibbs perspective, an irreversible process is one in which you take two ensembles at two different temperatures and bring them together, and there's a heat flow from one system to the other. And if you just let the heat flow, the process is irreversible. There's no way of making things go the other way. He does, however, also treat another way you could try to have irreversibility and don't. He says, let's look at a canonical ensemble. Let us select out of that canonical ensemble a specific subset of the ensemble in which there's been a fluctuation in some variable. For example, we will take the gas atoms in this room and we will select out all of the states of the ensemble in which the oxygen atoms are up near the ceiling and we're breathing nitrogen. Yes? And he then asks, what happens in time? And the answer is that the advance of time will cause the fluctuation to disappear with almost total certainty. However, that is equally true whether you look forward in time or look backward in time. If you take the fluctuation and you compute back in time from the moment when you have the fluctuation goes away. And therefore, if you want to say that this disappearance of the fluctuation is irreversible, it is equally irreversible in both time directions along the time axis. Another way of putting this is that you do not have irreversibility within the canonical ensemble, which should not be surprising because the ensemble describes the motion of particles that obey Newton's laws or Maxwell's equations or the Schrödinger equation, and guess what? Those equations are all time reversible. There are large numbers of people who have batted their heads against the wall because they try to pretend that Gibbs didn't show this. Life is cruel. It happens. In any event, we have now described irreversibility. The last thing he does is to discuss, and we are now to the start of Lecture 8, the last thing that Gibbs does is to discuss identical particles. Now, when Gibbs says identical, you hit...
It's still fine.
Okay. When Gibbs says identical, he just means that they're the same, like two bricks are the same. Quantum identical particles aren't around yet because there's no quantum mechanics. And he asks the question, we talked about this, but I'm going to add something to it. What happens if you have two states of the ensemble, one in which the two identical particles are here, and one in which they're switched? Are these two states of the same system, or is this the same state and it should only be counted once? And Gibbs quite specifically says, this is the same state, you only count it once. And if you do this, you get completely reasonable results. In contrast, Boltzmann said the opposite. Boltzmann said that if this is a state of system, this is a state of the system, and there are two different states of the system, and they get counted twice. The problem with this is something that is erroneously called the Gibbs paradox. And what the Gibbs paradox says is that if you have two identical volumes of gas, same temperature and pressure, and you connect them with a thin pipe, the entropy of the system changes actually quite considerably. And the statement, the entropy of the system changes, says, by opening and closing the valve on the pipe, the entropy of the system changes, the total entropy. Therefore, I can use this to drive a steam engine. Well, that's absurd. It's a perpetual motion machine. And the fact that this appears to be the case in the Boltzmann formulation is called the Gibbs paradox, even though Gibbs, 1, gets the answer right, 2, does not think there's a paradox there. In fact, the word paradox never shows up in his discussion because his discussion leads to the correct answer. Okay? And now we come to the one bit of identical particles that we did not discuss before. Right? We said if we take two particles and switch their positions exactly, it's the same state of the system. And classically, exact has a perfectly well-defined definition. The positions afterwards occupied by these two particles are the same as they were before, except I switched the labels. Quantum mechanics, however, puts a slightly different tone on this. That is, the two particles occupy some bit of phase space. They're within some delta x and some delta p, and they have been localized. But there is this result called the Heisenberg uncertainty principle that tells us you can't localize a particle in delta x and delta p at the same time to tighter than a certain boundary. Okay? In fact, there's the Heisenberg uncertainty principle, delta x, delta p greater than a number related to h, Planck's constant.
Isn't that because you can only know a particle's position or momentum at any given time? You can't know them both?
It's because the position and momentum operators don't commute.
They don't commute, so you can't measure both with total precision. However, you can say, I will set up a wave function. And the standard wave function is a Gaussian, because if it's Gaussian in x, it's also Gaussian in p. And having said I have set up a Gaussian wave function, which is the standard one on which the calculation is done, if I only localize the particle within some distance delta x, I can localize the particle within some distance delta p at the same time. And the product delta x delta p doesn't care how big delta x is. I can locate delta x with complete exactitude as long as I don't care what the momentum is at all. And I can locate the particle within delta p of 0 as long as delta x is infinite. That might be difficult to pull off, but it's not forbidden. And it is exactly because the operators are not commuting. However, we now come to the important issue. How, in the uncertainty principle, should you define delta? And the answer is, I mean, it's a Gaussian, so it has some half width at half height. But I could also say that delta x is 2 sigmas out, 3 sigmas out. If you're a modern industrialist, you talk about 6 sigmas. And you could put in various different definitions of delta. It's just a mathematical definition. And if you change the definition of delta, the constant on the far side of delta x, delta p greater than or equal to number, the constant in number that is multiplying h gets changed. H has to be there because you need a natural constant with dimensions action, momentum times position, energy times time. But if you change your definition of delta, clearly the number multiplying h is going to change. Yes?
Mm-hmm.
Well, there is one and only one point in physics that cares about the definition of delta. It is in statistical mechanics. In statistical mechanics, it's called the Kirkwood-Wigner theorem. We will get to Kirkwood-Wigner later in the term. In the Kirkwood-Wigner theorem, you actually do the calculation and ask, well, when we say two particles are identical, that really means they're each within a delta x, delta p box, the same pair of delta x, delta p boxes. How big are those boxes? And the answer is those boxes have delta x times delta p equal to h. Not h bar, not h bar over 2, h. And that is the one place in physics where the definition of delta comes in. It does not happen to be the same as the one that is usually done in quantum classes. So what this means is as follows. If you think of the partition function, we do this complicated integral, yes, and we're going to say q equals e to the minus beta a. Well, if q is equal to e to the minus beta a, what must the dimensions of q be? Unity, yes? So there's something I have skipped over in my definition of q, and it is buried in the definition of c, that extra constant. And the answer is the extra constant divides out how many phase space elements there actually are. And so for each product dx dp, each pair of integrals dx dp, you pick up a 1 over h. dx dp has units action, h has units of action, and therefore dx dp over h has units 1. For the ideal gas, then, the constant c has two pieces. It has the 1 over n factorial, because you can switch all those particles around. And it has a 1 over h to the 3n, because there are 3n pairs of classical coordinates that you're integrating over. And now q is dimensionless the way it's supposed to be. The proof that it's supposed to be h is this theorem, Kirkwood-Wigner, that we'll get to. And g, we now have a complete definition of q. Okay? Now we will push ahead to Lecture 8. And the objective in Lecture 8 is to discuss entropy. No, we did not just have another earthquake. The student kicked the camera. So having said that, let us start off a bit on the laws of thermodynamics. Historically, actually, the second law was derived before the first, but they're numbered in reverse order. So we'll talk about the first law first, even though it's later. And the first law goes back to James Joule. And what Joule did was to have a brilliant idea, because we are in the 1830s, and people have built coal-powered steamships, and someone has the idea of building a coal-powered steamship that could cross the Atlantic Ocean. The problem with this is that if you do the calculation using the available steam engine, you discover it's totally impossible to build a steamship that can cross the Atlantic. And you may wonder, gee, what did they miss? And the actual answer on what they missed is it was assumed the ship would be about the size of a contemporary coastal freighter, that is about 500 tons displacement. The drag would be large, the payload capacity of coal would be small, and if you try to build a 500-ton ship that can sail across the Atlantic, you really have to be fairly modern in your design. The great British engineer Isambard Kingdom Brunel got around this. He first built the Great Western, which is still afloat. It was found in the New Hebrides and brought back to England a decade ago. And he then built the Great Eastern, which was 720 feet long. It was bigger than anything else ever built. It did fine, except its engines we're coming to why in a moment, developed 1/3 of design horsepower at 3 times design fuel consumption. So instead of being able to go to Australia without refueling, it could marginally get across the Atlantic if the captain was careful. But it was slightly marginal as a design. In any event, Joule had the bright idea. He knew exactly how to solve this problem. He would replace this big clanking steam engine with a nice pretty electric motor and some D cells, batteries. And all he had to do was improve the electrical engine design until you had a couple of batteries sitting here, and you had a really, really efficient electrical engine that would do a huge amount of work and would take the engine, the ship across the Atlantic on a pair of flashlight batteries. He by and by found this wasn't going to work, couldn't be made to work, and eventually discovered that you could convert work into heat. And it didn't matter which form of work you used. If you did the same amount of work, force times distance in the simplest form, you got always the same amount of heat out. And therefore, while he wasn't very precise on saying work is energy, he was precise enough. The amount of energy you needed to heat something was linear in the temperature change. And he chugged off to a scientific meeting and gave a talk. And sitting in the back of the room was another physicist. And it was Thomson. Not the electron Thomson, another one. And Thomson pointed out this didn't seem to be correct because there was a known law of thermodynamics, which we would now call the second law. The second law was due to Carnot in 1800. And what Carnot said was that if you built a Carnot cycle engine, you take working fluid between 2 temperatures and use it to do work, you always get the same amount of work out, and by implication, the energy required to change the temperature by a modest amount goes as the square of the temperature, which contradicts Joule's result. It took a while to fix the fine details of why this didn't work. It probably didn't help that Carnot believed that heat is a chemical substance like mercury, and except that it could permeate things, and so you heated something by infusing it with heat, the way you make hot chocolate by infusing the boiling milk with cocoa. Yes? Well, Carnot had this somewhat mistaken idea, and it waited for Rankine to show that the fact that heat is not a chemical substance really doesn't matter, because nothing in Carnot's calculations or argument actually requires that it, say, be a chemical substance so we can form phlogiston dioxide, which you, of course, cannot do. So in any event, we formed the 2 laws of thermodynamics, and the first law is conservation of energy, and the second law deals with the behavior of entropy. And for once, I'm going to pull out some thermal results which you probably have not seen. And we go on to page 116, and I first start by writing the Helmholtz free energy A as kT minus kT log Q. That's simply the basic law of nature that Gibbs derived, except I've reordered the terms a bit. Okay. Now I introduce a thermodynamic statement, which is there's a thing called the entropy S, which is minus the partial of A with respect to T, under the conditions that you're keeping the number of molecules and the volume a constant. Those subscript things, constant N, constant V. You see the subscripts? They're very important. One of the standard ways people go wrong in doing thermal calculations is they don't bother to write down the subscripts, and they fail to notice that they held the wrong thing constant. Of course, sometimes saying I am holding something constant requires thought on how you're going to do it. For example, if I have a volume of gas sitting in this imaginary cylinder, and I am going to hold the pressure constant while increasing the volume of the gas. Yes?
Mm-hmm.
How can I possibly hold the pressure constant while increasing the volume?
Increase
Eh,
temp. Increase temp, right?
Yes, oh, you figured it out. I had a whole thermo class at Michigan, 130 students who looked there in dead silence. They couldn't imagine. Of course, they'd had engineering thermo already, so they were a little blinded as to how you do it.
I took engineering thermo already.
Oh, well, the answer is with a blowtorch. It works fine. Works every time. You have to be a little gentle to keep the temperature constant, but it'll expand. So, that is the answer. Well, actually, you don't keep the temperature constant. That's the whole point. You're going to keep the pressure constant, and therefore the temperature goes up. But there is the definition of entropy. Okay, what are we going to do with the definition? Well, we're going to take the derivative. So we're going to take the thermodynamic identity of equation 8.2 and apply it to equation 8.1. And if you do that, you get equation 8.3. And what actually happens to get there is that there's a partial with respect to t, and it can attack in two locations. It can attack the temperature, or it can attack the log Q. And if it attacks the temperature, you get the first term. And if it attacks the log Q, you get the second term. Okay. Well, that looks fairly bizarre. What can we do with it? Let's put in the definition of the partition function. That's 8.4. The partition function Q is the sum over all of the states, this constant C exponential to the minus beta energy. And so we plug it in. And in a certain sense, we are now done, but we are going to do a couple of things that are a little tricky. For example, Q is really a function of beta, 1 over kt. The derivative in 8.3 is a derivative with respect to temperature. So what we do is we apply the chain rule. And we say that d dt, the derivative with respect to temperature, is d beta dt. Now you want to think about that a bit because we've got lots of variables wandering around and you have to ask, is the chain rule okay? But in this case, beta is purely a function of temperature, so there's no way anything can go wrong when you apply the chain rule like that. And the chain rule, d beta dt, says d beta dt is minus k sub b beta square. There are lots of ways of writing it, but that's one of them. And therefore, dq dt, what do you get? Well, you have a constant script c. The d dt attacking the q, the only place it could attack originally is the exponential, so it brings down a factor of e, and it brings down a d beta dt, which I have written in. Okay. So we have that. And now we combine terms and get 8.6. The first term in 8.6 is a bit of a cheat. That is, I had to do something to get there. The first part of 8.6, the k sub b times minus beta aq, started out as k sub b times log of q. So I actually take equation 8.1, which is a is minus kt log q. I take its logarithm, and the logarithm gives me a, I'm taking the logarithm of e to the q equals e to the minus beta a, which gives me a minus beta a. And you see the minus beta a right there. The minus beta a is simply log of q. Then I would like to put everything over the same denominator. And to put everything over the same denominator, I have to multiply and divide by q. And so I do that, and now everything is over the same denominator, q. and the first term thus is multiplied by a Q, and I have 8.6. I have also dragged a common factor K sub B out in front. K sub B matters. Entropy has dimensions. Entropy has dimensions energy over temperature, because TS, temperature times entropy, is an energy. It's not a free energy, but it has units energy. And therefore, K sub B is always the dimensions of the entropy. Now, in our case, it will be joules per Kelvin is the units. You should realize there are European authors who set K sub B equal to 1. It's a dimensional choice. It means you are using some somewhat odd dimensional units. And so your dimension, your temperatures are in units of joules. That's perfectly all right. If K sub B is 1, your new temperature units are joules. The one obstacle to this you should realize is this says that at unit temperature, a single gas atom has an energy of 3/2 joules. In order to have this 3/2 joules, well, K sub B is a fairly small constant, yes? In order for unit temperature, the molecule has a temperature of a joule or so. The temperature in our normal units must be absolutely humongous. It must be numerically 1 over K sub B, which is 10 to some large number of degrees. So that says that all local temperatures are 10 to the minus something, very small number of degrees. That's very inconvenient. Yes? Okay, so we've talked about K sub B. And what do we now do? We now reach into the denominator, we reach into the numerator, and we replace the numerator Q with the definition of the partition function, which is 8.4. So in 8.6, we go in, and the minus beta A Q becomes minus beta A, that's just a number, times summation over all states C e to the minus beta E. Then the other thing we do is we reach into the denominator. The denominator is just Q. Well, Q is e to the minus beta A. And we're going to pull it up to the numerator as e to the plus beta A. That's legal. You know, 1 over e to the minus beta A is e to the plus beta A. And once we've brought it up to the numerator, we multiply it into all of the summations and reorder to collect terms a bit. And when I collect terms, I get equation 8.7. And equation 8.7 is, well, you can see it there. There's K sub B, a summation over all states. The constant C, beta. And then there's an E minus A exponential of minus beta E minus A. Yes? And that approaches, we're almost there. The last thing I do is to remember, what's the statistical weight of a single state of the system? Well, it's W. That's the letter we've been using for the weight, W sub J. And W sub J is the constant script C times e to the minus beta E minus A. That's the line right after equation 8.7. The e to the, it's actually, if you count plus minus signs, it's actually e to the plus beta A factor is the normalizing factor. It's the partition function. However, the normalized statistical weight is what I have just written down under equation 8.7. It's W equals. Yes? Take that definition and plug it into equation 8.7, and what do you get? You get that entropy S is minus K sub B, and now we sum over states, the statistical weight of the state times the log of the statistical weight of the state minus the log of the constant script c. And that is 8.8. And 8.8 is the Gibbs form for the entropy. 8.8 lets you calculate the entropy of the system. Yes? We're good? Everyone's happy so far?
Is there a specific reason why we can only calculate it in the Gibbs form instead of the other forms that we have?
Well, in fact, you could use the Boltzmann form. We'll get to that in a bit. And you might ask, well, can't we calculate it directly as an ensemble average? We're about to get to that. Now, when Gibbs wrote this down, he simply said that S is equal to K sub B times, except his K sub B was 1, times W log W. That's because in the Gibbs development, the constant script C is unity. And what's the log of unity?
0.
0. So in Gibbs development, if you'd asked him about script C, or log of C in this case, he would have said, well, it's the number 1 until my last chapter, and therefore log of 1 is 0, it disappears. Okay. There is a typo 2 lines down. The last full line of the paragraph, including 8.8, Gibbs finally demonstrates C equals n factorial to the minus 1. That is, Gibbs demonstrates the constant C is 1 over n factorial. It's not n factorial. And now we come to the riddle. Suppose you thought, okay, we're going to calculate the entropy. So let us go into the system and do an ensemble average. Sounds good, doesn't it? So we write down the entropy of each state of the system and do an ensemble average exactly as shown as in 8.9. And there's only one little problem like that. Entropy is not a mechanical variable. You can write down 8.9, which is that the entropy is some weighted average of Sj, the entropy of each state. But you can't do that because you cannot assign an entropy to a state. Why not? Entropy is an ensemble variable, not a system variable. The entropy, like the temperature, which we went over in thermometry, are defined for the ensemble, but if you ask what is the free energy in this state of the system, within the canonical classic statistical mechanics, there's no answer to that question. Okay, so having said this, we now look at some special cases. In the first special case, since we are chugging along in time, I am going to give you an outline and make a homework problem. And if you want the homework due next Wednesday, that's just fine. Okay, we go to equation 8.10. Equation 8.10 is the partition function of the ideal gas. And it's the partition function you've seen all along except for two things. First, I've written out explicitly the 1 over n factorial. It's a monoatomic ideal gas. All atoms are identical. Second, I stuck in what we discussed at the start of lecture, the h to the 3n, and the h to the 3n refers to the fact that if two atoms are within a box that's less than delta x, delta p on a side, they cannot be told apart by their position and momentum. Now you might say, how big is delta x and delta p? It's only the product that's constrained, and you could change the shape of the box if you want to. And what then happens from 8.10 is that you do various substitute derivatives and work hard and think carefully, and you can get to equation 8.12, which is the Sakura-Tetrode equation. Yes, and the first way to get there is you say I have Q, so I know the free energy A, and I take the derivative of the free energy A with respect to T, and if I'm clever with my constants, I can get 8.12. Okay? Now that isn't, since I'm nice, we're going to do this twice, I then say, let's do this again. Let's calculate the entropy of the system, and this time we're going to calculate the entropy of the system by rearranging the Gibbs form, and you sort of chug through from 8-13, and you get to 8.16, and if you actually do all these things, you have to know what the free energy A is. It's K sub B log Q, etc. You can get to 817. No, 817 is not a new entropy. 817 and 812 are the same equation, derived two different ways. So far, so good? Okay. Now we're going to consider, and we are going to get to the Boltzmann form for the entropy. And the notion is as follows. Suppose we have a physical system. Suppose it is very, very cold. In that case, quantum mechanics will come in, and there are some number of ground states, and there are some number of lowest excited states. But if kT is really small, the system never goes into those excited states. It's only in the ground states. Because those are the ground states, they all have exactly the same energy, and therefore whatever their probability is, it's exactly the same for all of them. Sound plausible?
Mm-hmm.
It's exactly the same for each of them, I should say. Well, what is the likelihood of each of those n ground states if it's normalized?
1 over n.
Yes, the likelihood must be 1 over n. So we're going to say W sub j is 1 over n. And we are going to plug W equals 1 over n into the Gibbs form for the entropy. And in particular, we are going to plug it into equation 8.8. S is minus K sub B sum W log W. Well, there are capital N terms. They are all identical. Each of them has a 1 over n in it, but you get n of them. So the n and the 1 over n cancel. You have n states, each with a weight, each with a probability 1 over n. And you end up with G. S equals K log n. You end up with equation 820. You don't have a script C because Boltzmann didn't know about it. And S equals K log n, different notation, is the Boltzmann entropy. And so the Boltzmann entropy works just fine if all states have the same energy, which was his basic assumption. Now, where could you actually get large numbers of states that are all the same energy? Well, I give an example. Suppose we have a crystal. It's a crystal of hydrogen gas, but the hydrogen gas in question is hydrogen deuteride, HD. The molecules are little footballs or vitamin pills, and they line up parallel to each other. However, the states in which the D is at the top and the H is at the top have the same energy. So we have a state like this, and we have a state like this, and we have what are the states of the system? It's all possible combinations of an H and a D being up or down. So if there are n molecules of HD, how many states do they have? How many states does the crystal have?
Factorial?
Well, actually no, it's not n factorial. It has one for each combination of up and down for each atom. That looks exactly like a binary number. The number of states is 2 to the n. Yes? So the number, I'm cheating, don't worry. I'm actually cheating, but we won't see that for a second. The number of states is 2 to the n, and therefore, if I say the number of states is 2 to the n, the probability, I can go into the Boltzmann form, S equals k log n, and I put in the fact there are 2 to the n states, and I get S equals k sub b n log 2. Right? And there is the energy of the HD crystal, and this is the standard solution you would be expected to have gotten from statistical mechanics classes. Of course, it's wrong. Why is it wrong? Well, H2HD's parallel and anti-parallel do not have the same energy. And therefore, if I actually make this crystal by freezing hydrogen deuteride gas, and if I am actually very careful and freeze it in such a way that it goes to the lowest, the correct states with the right thermal probability, it is always in the correct state, which if I recall correctly is in the interdigitated one. And how many states are there in which the hydrogen atoms are doing exactly this: up, down, up, down, up, down, up, down?
1. Oh, 2.
2. Because if you pick up the whole crystal and turn it upside down, there is a second state whose energy is equal to the first. However, if there are 2 states, that says the entropy is k sub b natural log of 2, which is smaller than the first number we calculated by a factor of 1 over n.
Mm-hmm.
That's important because that's the third law of thermodynamics. The entropy of a system at absolute 0 is 0, which says there should only be one ground state, or very close, and therefore the entropy is far less than n log 2, which we initially calculated. You should, however, realize that getting from n log 2 to log 2 is hard, because by the time you have frozen the hydrogen gas and you have hydrogens with the wrong relative position and they're inside a crystal, in order to flip one of the hydrogen atoms to get equilibrium, you have to find enough thermal energy to do this, because you have to push all this other stuff out of the way for a moment. It's not available, at least not very easily. And therefore, on reasonable lifetimes like the age of WPI, the lifetime of the universe, well, maybe not the duration of the average doctoral program, but the lifetime of the universe anyhow. No one laughed at my joke. Well, it's not going to happen, and therefore, if you want to equilibrate this thing, you have to do something clever. Now we come to the last bit, because we are out of time. You remember we talked about identical particles?
Mm-hmm.
And there is a factor of 1 over n factorial, which goes into that script C.
Mm-hmm.
Where did the 1 over n factorial go? That is, why is it k sub b n log 2 rather than k sub b n log 2 minus n log n, or something like that? Answer. We counted how many states there were. Remember I said there were 2 to the n? We're going to construct the ensemble. The first molecule may go in any of the n slots in the crystal lattice.
Mm-hmm.
The second may go in any of the n minus 1. The third may go in any of the n minus 2. And therefore, the number of states is not 2 to the n, it's 2 to the n times n factorial, which is a slightly larger number. But when you notice that it's 2 to the n factorial, and remember that the atoms are indistinguishable, it all evens out. And you do get back to equation 8.21. You may readily find physics authors who get this wrong and claim that atoms in a crystal are distinguishable, as though the laws of quantum mechanics could tell what the solid state was. Oh, I gave you derive the Sackur tetrode equation. There are 2 forms of that. And do also equation 8.3 cold crystals for monodeuterobenzene C6H5D. It's a hexagon with 1 deuterium lying off to the side.
What was the first problem?
Oh, the first problem,
We're deriving 812.
you're deriving 812 from 810, and you're deriving 817 from, oh, it actually goes back to 814.
So 817 from 814?
Mm-hmm. And 812 from 810. We are now done.
And then the 2 that you just mentioned at the end.